Alright, today we're talking about chapter 6, section 1, the definition of an nth root. Alright, so the definition of a square root. So we're talking about, today we're going to talk about nth roots, right? Just basically roots. But first up is square roots. And square roots we know as the, um, we're looking for, well, let's just do a definition. One moment, let me snip this. Alrighty, so the the reverse operation to squaring a number is to find a square root. So for example, finding the square root of 36 is equivalent to asking, when squared, what number equals 36? So the one obvious answer would be 6, right? Because 6 squared is equal to 36. But negative 6 will also work because negative 6 squared is equal to 36. Right? And notice how we have both the positive 6 and a negative 6. All right, we'll be coming back to that later on in this, probably in this chapter. So later on in this chapter, we'll come back to that positive and negative solution. But for now, let's try to work out example 1. Example 1 reads, one moment, I got my cord. There we go. All right, so number 1 reads, identify the square roots of the real numbers. So A is 25. So what is the square root of 25? So well, when squared, what is equal to 25? All right, well, that would be 5, right? 5 times 5. B, all right, 49, when squared, what is equal to 49? Well, that would be 7, right? 7 times 7 is equal to 49. C, when squared, what times what is equal to 0? Well, that's just going to be 0. And then lastly, and this one's a tricky one, right? So when squared, what uh, what will give me negative 9? All right, well, we know that a negative times a negative is a positive, right? So we don't really have a number. There is no real number that will equal to negative 9, right? So we would say that there are no real number. And we're just going to put no real number in our n, right? So that's how we do just finding square roots. And I'm pretty sure, one moment before we begin, okay, good. We have a chart for the roots. All right, next up we're going to talk about our radical sign. All right, so recall that the positive square root of a real number can be denoted with their radical sign, right? The radical sign is just basically, saying well, it's not necessarily always square root. It's the root, but not necessarily the square root, right? The square root, well, let's see, if it's by itself, then yes, it is a square root, right? But if there's a 3 here, we say cube root. If there's a 4 here, we say fourth root. If there's a 5 there, fifth root, and so on. Anyway, starting up here. So let a represent a positive real number, then the radical sign a is a positive square root of a. Okay, notice that there's no number right there in that little hole. So if there's no, again right here, so I'm looking at, since there's no number there, then it is indeed a square root, right? The positive square root is also called the principal square root. And then for the second, don't really name anything, but number 2, negative square root of a is just simply the negative square root of a. And then we have the square root of 0 is equal to 0. Alrighty, so example 2, a, this reads simplify the square roots. So uh, before we do actually get to this, let's do this. Let's write down a list of our square roots that I feel like are very common, right? And I believe going 1 through 10, really. So So 1 squared is going to be equal to 1. 2 squared is equal to 4. 3 squared is equal to 9. 4 squared is equal to 16. And honestly, I think we can just do 12. Let's do that. And then we've got 5 squared is equal to 25. Now, as I write these down, these are the square roots that you need to memorize. I say that because you're going to need to be able to recall this information very quickly. And then 12 squared. Right. So these are the first 12, and I think they will serve you very well. These are the ones that we're going to be using quite often, and then we'll see that, of course, starting in this particular example. All right, so we had the square root of 36. Okay, so we would say, you know, what times what is equal to 36? Well, we know that the square root of 36 is going to be equal to simply a 6. Okay, and then B is not necessarily tricky, but a tad tricky, mainly because we have a fraction in there, right? And of course, I've told you before, I don't like fractions. I doubt you like fractions. Nobody likes fractions, right? But here we are. But if we started this problem with the square root of 4 over 9, we know that we can split that up into the square root of 4 over the square root of 9, right? And then from there, we know the square root of 4 is 2. I'll put this down here, I guess. Well, yeah. Well, the square root of 4 is 2, so we'd say 2, and the square root of 9 is 3, so 2/3. Right. And then C is probably one of those that, you know, you probably need a calculator for, but it's not too difficult. We have the square root of 0.04. Well, what times what is equal to 0.04? Well, that would be 0.2. 0.2, yeah, 0.2. Alrighty. Example 3, we're going to be simplifying more square roots, and these really drive the point home of the negative signs. Okay, so let's start with A. We have the square root of negative 144. Okay, well, we've seen 144 before somewhere, haven't we? We saw it here, so it's a good thing I did go to 12, right? So I know that 12 squared is indeed equal to 144. Right? However, this is saying the square root of negative 144. All right. Well, what is the square root of negative 144? Well, what times what gives you a negative 144? The answer to that is no real number. No real number, if you multiply it by itself, will give you negative 144. And of course, we say real number because there is obviously a concept that we're familiar with called complex numbers or imaginary numbers that do work, but we're not into that just yet. But I'm pretty sure you've heard of them. All right, B looks pretty similar, but it's not. All right, because we have the negative sign on the outside of the radical. So what we're saying is, okay, so what is the negative? The negative, well, I can't make that straight for anything, can I? There we go. No, that's not it. We're just going to stick with that one. What is the negative square root of 144? Okay, well, we put the negative sign there. It is independent of the radical sign. And what is the square root of 144? Well, it's 12, right? So we'd say just simply a negative 12. Right? And then C, what is the square root of negative 0.01? Well, again, we have the same issue. We don't necessarily have that there is not a real number. When you multiply it by itself, that will give you negative 0.01, right? So same thing, no real number. We're having a lot of these. And then D, we have the square root of negative 1/9. Well, same thing. The negative sign's on the outside, so we can say the negative square root of 1 over the square root of 9. Well, what's the square root of 1? Well, that's just 1, so negative 1 over 3, negative 1/3. Okay, so I think all this deserves its own page. All right, so this is very important stuff, so I'm going to have to do the thing that I hate, and I'm going to have to just basically read off this board here. Okay, so the definition of an nth root. So finding a square root of a number is the reverse process of squaring a number. We know that. So this concept can be extended to finding a third root, called a cube root, or a fourth root, or in general an nth root. Nth root being, what in number of times, right? So b is an nth root of a if b raised to the nth power is equal to a. Some examples. 2 is a square root of 4 because 2 squared is equal to 4. 2 is a third root of 8 because 2 cubed is equal to 8. And 2 is a fourth root of 16 because 2 to the fourth is equal to 16. Right, so these are basically just nth roots. And then the radical sign, as I spoke about earlier, we use that to denote the principal square root of a number. So if we have some symbol and we put the n up there in that little nook there, is used to denote the principal nth root of a number. In the expression n, the nth root of a, n is called the index of the radical, and a is called the radicand, and I'll be using those words quite often in this particular course. For a square root, the index is 2, but it is usually not written, with a 2 there, right? We simply just put the radical sign there. A radical with an index of 3 is called a cube root, and we put the 3 there. So how do we evaluate our nth roots? So if n is greater than 1, right, and is an even number, then the nth root of a is the principal positive nth root of a. So basically just, if it is if it's an even number, right? If we have an odd number, then the nth root of a is the nth root of a. And then we have our examples. Now, I had you write down the square roots that we use quite often. Well, here these perfect cubes, perfect fourths, and perfect fifths. Definitely all 5 of the perfect cubes. And honestly, I don't really remember going too much further than the first 3 of the fourth powers, and then the fifth power is maybe the first 2, right? However, if you do have the brain power, the brain capacity, it will help you to quickly solve problems in the future doing it this way. But definitely all 5 of these, maybe the first 3 of the fourths and first 2 of the fifths, if you have limited computing power, especially here we being in the middle of the semester. All right, so this reads, simplify the expressions if possible. Okay, so starting with A, we have the square root of 4. Okay, well, what times 1 is equal to 4? That's pretty easy. That would just be 2. Square root of 4 is 2. B, we have the cube root of 64. Well, what times what times what will equal to 64? Well, that would just be 4, right? Because 4 times 4 is 16, and 16 times 4 is indeed equal to 64. C, we have the fifth root of a negative number. Okay, so previously, on the previous examples, when we had a negative number, well, let's circle in white, let's do it in red. We had when we were trying to find the square root of a negative number, right, negative 9, we said it was no real number. Okay, well, there was no negatives there, but we had the negative 144 and then negative 0.01. We said that those were no real numbers, right? Well, oh no, oh shoot. Well, those circles are staying. No, actually, I'm going to go ahead and erase those. No, I'm not. They're just going to stay. Well, C is not automatically not a real number because this is an odd index. right? It's 5. So it's basically saying what times what times what times what times what is equal to a negative 32, right? Well, there is a number when you multiply it by itself 5 times that will indeed get you a negative number, right? And that number is negative 2, because negative 2 times negative 2 times negative 2 times negative 2 times negative 2 is indeed equal to negative 32. Right, so first, before we proceed here, let's look at the fifth powers, right? 2 to the fifth is equal to 32, right? That's a positive 2 raised to the fifth power. I'm saying a negative 2, right? Because negative 2 times negative 2 is equal to 4, and this is equal to 4, right? 4 times 4 is 16, and the 16 times a negative 2 is equal to negative 32. So with that all said, just because you see a negative number inside your radical, or just because the radicand is a negative number, that does not mean that the solution is no real numbers. In this particular case, since the index is an odd number, we know that we do indeed have a solution this time. Right, in D, we have the fourth root of 81. Well, from the previous page, we know that 3 times 3 times 3 times 3 is equal to 81. Looking at the perfect fourth powers there. E, all right, with the sixth root of 1 million, that's just going to be 10. F. All right, now F is a square root of a negative number. So now we will indeed say no real number. Okay, and same thing we say for G also, right? Because, well, we have 4, which is an even number, and my radicand, that number inside, is a negative number. So we again say no real number. Right, so roots of variable expressions. Finding an nth root of a variable expression is similar to finding an nth root of a numerical expression. For roots with an even index, again, the index being the number that is right here. Right, if it has an even index, where am I at? I don't know, I lost myself. However, particularly, wait, where am I at? Let's just start over, sorry. So, finding an nth root of a variable expression is similar to finding an nth root of a numerical expression. For roots with an even index, however, particular care must be taken to obtain a non-negative result. So, evaluating the nth root of some a raised to the nth power. If n is a positive odd integer, right? So basically, if my index is odd, as well as my exponent inside, if they're both odd, then my solution is just basically the base, which is a here. If n is a positive even integer, right? Again, the n's match if n is even, as well as the exponent inside, then we take the absolute value of a. Okay, so looking at a, we have the fourth root of negative 3 raised to the fourth power. Okay, well, the 4 there is an even number, so we're going to be looking at principle number 2 here, right? So since it is even, we take the absolute value of my base in there, which is negative 3. So we would say the absolute value of negative 3, which indeed is just equal to positive 3. Okay. B, we have the fifth root of negative 3. Well, since 5 is an odd number, we're just going to take the base there, which is negative 3. C, we have it is written like this, x plus 2 and then squared. And then we know that right here is an implied 2, right? And since the 2's, since they're the same, they are both even, so we can take the absolute value of both. So we would say the absolute value of x plus 2. Okay, and then d, well, d might be a little tricky, right? Not necessarily, but why is that a, hmm, I don't think that is right. D. Yeah, okay. So, all right, so here's a typo. I know it didn't seem right for this particular lesson. We can obviously solve D, right? It's not we can solve it. However, it's not in line with the spirit of this particular lesson. And we see down here that it is indeed supposed to be a 3. So I'm just going to go ahead and snip this D. And heck, I'll just go and snip the E as well, because I was kind of running a little bit low on space there. So I'll snip those. Oh, that's good. I was wondering why they're going to throw a curveball in there like that. There. Okay. So this is supposed to be the 6th root. I'm just rewriting it. It's supposed to be the 3rd root of a plus b cubed. Okay. Well, anyways, since both the threes are odd, we see that we don't really change anything. It's just odd, right? And then E, I said I ran out of room for it because, well, I did. So I just snipped it, but it's not that hard to follow along. So if we have the square root of y to the 4th, right? We know that is a square root, right? We know that is a 2, an implied 2 right there. Well, we know we can change. We can break down y squared. I'm sorry, y to the 4th to y squared squared. So that means my exponent 2 matches up with my implied index 2, which I could take the absolute value of y squared, and then anything squared is even anyway, so we can just simply say y squared. Hmm. All right, I'll snip this, but I'm not necessarily going to go over it because I'm going to go over it pretty well with this example. I think these next few examples are doozies, so it's always good. Okay. So A, we are asked to simplify the expressions, assume that all variables are positive real numbers. Okay, so we have the square root of y to the 8th. Okay, so if I have the square root of y to the 8th, I know that that can be written as the square root of y to the 4th. Let's fix that. Y to the 4th squared. Okay, and then of course, since I have the implied 2 here as well as the 2 here, I know that this can just be equal to y to the 4th. B, one moment. Okay, all right, so B, we have the cube root of 27a cubed. Okay, well, I know that my 27 is a perfect cube, right? Going back to this chart that I asked you to memorize. 3 cubed is equal to 27. Okay, so this can really be written something like this: the cube root of 3 cubed a cubed. Okay, which can just be broken down into simply 3a. And C, we have the fifth root of a to the fifth over b to the fifth. Well, that just goes back to the previous example, right? I can just simply write that as a over b. And then d is indeed a doozy. D for doozy. All right. Now, the negative's out in front, so we're just going to put the negative out there right now. And then it is the fourth root of everything inside. Okay. So we can rewrite this as the fourth root of, and let's make that a little bit bigger so I can not smush my numbers. All right. 81. All right. So 81 can be written as 3 to the fourth power. And of course we have x to the fourth power. And then y, I can write that as y squared to the fourth power. Oh, that's horrible. Let's try that again. Y squared to the fourth power. That's better. Right. And then 16, I know I can write that as 2 to the fourth power. Okay. And all those inside are raised to the fourth power. So I can pretty much just simply say we're going to have a negative. Again, the negative's on the outside. A negative 3x y squared all over 2. Because everything inside is to the fourth power. All right, so the Pythagorean theorem, so we'll go and snip that with the problem. Use the Pythagorean theorem. Okay, so we're going to need to actually snip the triangle there. Okay, so snip this in 2 here. So I was talking to my uncle one day, and he's not really, I mean, he's a brilliant man, but he hasn't taken a math class in, he's like maybe 30, 35 years, right? But one thing he did remember was the Pythagorean theorem. A squared plus b squared is equal to c squared. So kind of like how the you cannot divide by 0 sticks with you, at least hopefully it does. The Pythagorean theorem also kind of sticks with you, right? So starting from the top up here, we have given a right triangle with legs of length a and b and hypotenuse of length c, the Pythagorean theorem can be stated as a squared plus b squared is equal to c squared. So if we have leg a and leg b, all right, c is always going to be the hypotenuse. The hypotenuse is the length opposite of the right angle being the 90-degree angle. It doesn't matter what a is, doesn't matter what b is. It only really matters what c is. Okay, and c is always going to be the hypotenuse. And looking at this example, c is 13 there. Okay, so when we begin to solve this problem, we're going to have to set it up using the Pythagorean theorem. And we're going to do that like this. So we know that the Pythagorean theorem is a squared plus b squared is equal to c squared. Okay, well, I said it doesn't matter what a is, so we're just going to do a, we're going to do b, but it only matters really what c is. We're going to say c is, well, we're not going to say, c is 13. So we'll plug those in, right? So we'll say 5 squared plus b squared is equal to 13 squared. Okay. 5 squared is 25 plus b squared is equal to 169. Right. And then I'm just solving for b here. So I've got b squared is equal to 144 because I subtracted 25 from both sides. All right. And so now we're going to ask ourselves, okay, so what squared will give me 144? Right? Well, I went over that previously. I said memorize the first 12. Well, here we are. So b must be equal to 12. Right? And that is the Pythagorean theorem. Right? So now let's apply the Pythagorean. I think there's 10 of these, yeah. So let's apply the Pythagorean theorem. kind of the in the same way, right? There's not much different from this particular problem, and just simply solve for the triangle that we did on example 7. But we'll do it. So this reads that two boats leave a dock at 12 noon. One travels due north at 6 miles per hour, and the other travels due east at 8 miles per hour. How far apart are the two boats after 2 hours? Okay. Well, if they are traveling at those speeds, and of course, there's no water resistance or wind resistance or anything like that. We know if you're traveling at 6 miles per hour after 2 hours, you're going to be going 12 miles. Okay. And of course, if you're traveling at 8 miles per hour after 2 hours, you're going to go 16 miles. Right. And then we're just basically multiplying the miles per hour by 2. So we need to figure out how far apart they are. Right. Well, this is just simply a squared plus b squared is equal to c squared. And we're told, in this particular case, a is going to be 12. So we'd say 12 squared plus 16 squared is equal to some c squared. Okay. Well, 12 squared is 144 plus 16 squared is 256. And that's equal to some c squared. Well, 144 plus 256 is equal to 400. It's equal to c squared. And then we ask ourselves, what times what is equal to 400? Right? So in this particular case, we would say that 20 times 20 is equal to 400, or in other words, c is equal to 20. Now, let's see. I didn't do it on this page because we haven't gotten to that point yet where we solve things from square root. But if you're thinking, and if you recall from high school or whenever you did take mathematics, that like on this particular example, you can take the square root of both sides. Okay, we can do that as well as over here, take the square root of both sides, right? But we end up with a negative number sometimes, but we disregard it. Now again, I'm probably just spitting out way too much right now, so let's just stick with what I just said here, and then whenever we get to that solving with a radical, we'll discuss it further then. But for now, just kind of ask yourselves, okay, so what times what is equal to 400, and then go from there. All right, so looking here, we've got if n is an integer greater than 1, then a function written in the form f of x equal to the nth root of x is called a radical function, which we know. Well, we don't. I wouldn't say we know. It's implied. When we have f of x, we know it's a function. When we have a radical in there, it is a radical function. So note that if n is an even integer, then the function will be a real number only if the radicand is non-negative. Therefore, the domain is restricted to non-negative real numbers, or equivalently 0 to infinity. So what does this mean? What this is saying is the domain, if you recall, the domain of a function are the numbers that I am allowed to use, right? So let's take a trip back real fast, and let's say 3 over x minus 9. If this were a function, the domain of this function would be every single number in the entire universe except for one number. And that one number would be when x is equal to 9, because 9 minus 9 is equal to 0, and we cannot divide by 0, right? So the domain of this particular function is every single number but 9. I can use any number. X can be any number here except for the number 9. Once it's the number 9, we're dividing by 0, and it's no longer, it just will not work. So kind of the same process or mindset here. If we have the a radical, the nth root is some radical, then the domain is going to be, well, if it's even. If we have an even, if this is even, then the domain is from 0 to infinity. I can only take the nth root of numbers that are positive and 0. Okay, of course we know that because we've seen plenty of examples in this section already where we try to take the square root of a negative number. We cannot take the square root of a negative number. There's no real number that exists, so it's out of the domain. All right. But if it's an odd number, then it doesn't matter. Then if it's an odd number, the domain is all real numbers. Okay, because we have seen before that we can indeed take uh, the nth root where n is an odd number of a negative number. Okay, so looking at A, we have g of t is equal to the fourth root of t minus 2. Okay, so that 4 is an even number, so this tells me that my domain is going to be from 0 to infinity. So what I must do in order to figure out what this domain is, and you only do this when you have an even index, then it's going to be t minus 2. We're going to set that to greater than or equal to 0. And then if we solve, we say t is greater than or equal to 2. And therefore, my domain here is going to be from 2 to infinity. So what did I just do here? Well, 2, and then it's actually a bracket. Sorry about that. So what did I just do here? Well, I know that what's inside this the radical, all right, or in other words, the radicand, I know that that must be, all right, never mind the t minus 2. I know that what's inside the radicand must be 0 or greater, right? So what I have to do is I set up the radicand to greater than or equal to 0. And then I just solve. That's it. So I just solve. And when I solve, I get t is greater than or equal to 2. And then if I write that in the interval notation, then it's just simply 2 to infinity. And of course, remember we put the bracket there when we have the or equal to symbol. Okay, b, well, b is the cube root of a minus 3. Well, if it is, and again, if we just turn attention up here, we see if n is an odd number, then the domain is all real numbers. So since this is the cube root, or a 3, then we're just going to put negative infinity to infinity, right? It's all real numbers. And then C is a little more tricky, and I think I might have room. I don't know. We'll try it out. Okay. Well, it is the square root of 3 minus 5x, all of that plus 2. So I'm really only concerned with what's inside the radical. So what I'm going to do, again, I'm just going to set what's inside my radical, 3 minus 5x, to greater than or equal to 0. And then I'm going to solve. So let's see if I can do this in my head. Put negative 3 on the other side, so I have a negative 5x is greater than or equal to a negative 3, and I divide both sides by negative 5, so I flip the sign, so I'm going to end up with an x is less than or equal to, less than or equal to 3/5. Okay. So x is less than or equal to 3/5, and if I wrote that as a domain, let's put this up here, or I'm sorry, in an interval notation, then I would say we'd go from negative infinity to a positive 3/5, and of course we also use a bracket there. And that's how we do, that's how we do C. Right? So you really only have to do this, I say really only, you only have to do this whenever you have an even index. The index is that number right there in the little crack. And of course, if you don't have a number there, it isn't applied to. But if it's an odd number, then it's just all real numbers. Super duper easy. And lastly, we're going to graph this, and I'm just going to snip this entire problem so we can just go ahead and, because their graph looks a lot better than mine, just being honest. And on the homework, you will have a graphing, I wouldn't say graphing utility, well, I guess you do, graphing utility on your homework. Oh, I guess I could have wrote the domain. Okay, well, it's here now. So this reads, so given f of x equal to the square root of 3 minus x, we need to write the domain of f in interval notation. So again, we just take what's inside the radical, 3 minus x, and set it to greater than or equal to 0. We solve for x, and we end up with x is less than or equal to 3. and therefore we can just write the domain as -infinity to +3. And then if we wanted to graph it, then we can just simply create an ordered pair, and we just plug x values into our function. So if we plug in as 3, well 3 minus 3 is 0, the square root of 0 is 0. We plug in a 2, 3 minus 2 is 1, the square root of 1 is 1, and so forth. And then we can end up graphing our function. All it is just creating a table. What do I plug into my function? What do I get out of my function? And then these are my points, and I proceed to graph. Now, I did kind of hand wave that because later on we're going to learn how to memorize what these functions are and just graph them just simply off of memory. And that concludes today's lecture.